We've looked at the algebra of matrices. Now let's see how that is related to the algebra of determinants. The first result we have is that the determinant of a product of matrices is the same as the product of the determinants. So the determinant of AB is the same thing as the determinant of A times the determinant of B. Now, a lot of useful results follow from this, including the three basic results on elementary matrices. The elementary matrix properties can be proven based on just this one rule here. Furthermore, if you have the determinant of, say, a scalar multiple of a matrix A, by repeated application of elementary matrix number 2, the scalar multiple of a row, this scalar will come out of the determinant, but we need one of those for every row in the in our matrix. So if there are n rows in the matrix, we get c to the n times the determinant of A. So for example, if we've got, say we wanted to do the determinant of the matrix 3, 6, 9, 3, 12, 15, and then 0, 0, 9. I see that we can divide all the rows by 3. So what we'll do is we'll factor out a 3 from the first row, factor out a 3 for the second row, factor out a 3 for the third row, so we've got 3 to the third, times the determinant of a matrix that's a lot simpler. We divide the first row by 3, we divide the second row by 3, divide the third row by 3. So we've taken this, this more complicated matrix and reduced it to one that was easier to deal with. Okay, we also have the property that involving inverses. So if A is invertible, that means that it has an inverse. So A inverse exists. And we know that A times A inverse is the identity. So if we take the determinant of both sides of this equation, this says that the determinant of A inverse, is equal to the determinant of the identity. Now the identity is a triangular matrix, so its determinant is easy to evaluate, and that's 1. Okay, now on the left-hand side, we can use our multiplication property and rewrite this as the determinant of A times the determinant of A inverse. This tells us that the determinant of A inverse, if we solve for that, the determinant of A inverse is the same thing as 1 over the determinant of A. So A is invertible only if the determinant of A is not 0. So that's actually a big deal down the line. The determinant of A is non-zero if and only if A has an inverse. There are often times that we'll see down the line where we want to determine whether or not we should even proceed doing the problem, and this determinant gives us a relatively quick test to do that. Okay, and our one final result we have in here involves transposes. We discussed this previously, and that's the determinant of a transpose is equal to the determinant of the original matrix. So we're going to use these properties in solving systems of equations, and we'll leave it at that.